Hello everyone, welcome back. My name is Mr. Kovalt, and in this video I'm going to be talking about how you can find the percent composition of your hydrogen peroxide when you're given the amount of gas or oxygen gas that's collected over water. So let's get into this. So in this problem we're given a 0.85 gram aqueous solution of H2O2, hydrogen peroxide, and it is decomposed into water and oxygen gas as shown below in this equation right here. And so the oxygen gas is collected by water displacement, which means it's collected over water. So the temperature of the gas collected is 26.0 degrees Celsius, and its volume is 38.2 milliliters when measured at atmospheric pressure. And so I actually skipped over a part that says because we are collecting it by water displacement, the mixture, the gas that we're going to get or that we're collecting is a mixture of oxygen and water vapor, but we're only interested in the oxygen gas, right? So we want to know how much oxygen gas was collected, and the water vapor is something that we need to abstract or subtract out of the total pressure that we are going to collect. So we're given a few things. So we're given that we start with a 0.85 gram sample of the aqueous solution. So we're going to have to use that later to find the original mass percent of the H2O2 solution. And so probably the first thing we're going to need to do is get the moles of the oxygen gas that was created or formed in the reaction. And so what we need to do is figure out what the pressure of the oxygen gas that we have. So one of the things that the data that we need to know is that vapor pressure of water. Usually this is given in a table, right? So you're given a table where you can find what the water vapor pressure is at various degrees Celsius. And so I pulled out of the table the one that we're interested in, since we are at 26, where's the temperature? 26.0 degrees Celsius. We want to know what the water vapor pressure is going to be, or what the pressure of water vapor is going to be at that temperature. And so for 26 degrees Celsius, that's going to be 25.0 millimeters of mercury. So we're going to have to subtract that from the total pressure that we have. Okay, and so the other piece of information is we're given the volume, 38.2 milliliters. So that's the volume of the container, that's the volume of the gas. And again, this is going to be a mixture of the oxygen and water vapor. And so it's going to be regardless of whether it's a mixture or not, it's still going to be 38.2 milliliters, because remember, both gases are going to fill up the total volume together. Remember Dalton's law that the one gas doesn't really affect the other gas, so their partial pressures are not going to affect each other. So we can subtract out the partial pressure, and the pressure of the oxygen is still going to be whatever it is. So remember that. And so the other thing we have is the fact that this is measured at atmospheric pressure. So at atmospheric pressure, atmospheric pressure is 760 millimeters of mercury. So that means that the mixture, right? So the pressure of the mixture of the gas has to be equal to the atmospheric pressure. And so that means that pressure of the atmosphere is equal to the pressure of the water vapor plus the pressure of the oxygen. which is going to be equal to 760 millimeters of mercury. Let me make this better. Okay. And we know that from our table, we know that the pressure of the water vapor is 25.0 millimeters of mercury. So that means that the atmospheric pressure, 760 millimeters of mercury, is equal to the pressure of the water, which is 25. So that's going to be 25.0 millimeters of mercury plus the partial pressure due to oxygen. So to get the partial pressure of oxygen, we just subtract out 25.0 millimeters of mercury from both sides. And here we get the partial pressure of the oxygen that was produced from the reaction is equal to 735 millimeters of mercury. Okay, so we have pressure, we have temperature. Where's temperature? We have temperature. I'll write that over here. Temperature is equal to 26.0 degrees Celsius. We would need to convert that to Kelvin. So we're going to add 273.15. And so that's going to be equal to 299.15 Kelvin. So we've got our temperature. This we would need to convert to atmospheres. So if we take 735 millimeters of mercury over 1, and then we're going to use our conversion factor of 1 atmosphere is equal to 760 millimeters of mercury. So 760 millimeters of mercury goes on the bottom and 1 atmosphere on top. So millimeters of mercury cancels out. And then when we calculate that, we get 9671. So 0.9671 atmospheres. Let me just double check that. 9671. That's correct. So we got our pressure in atmosphere. So this is the pressure of our oxygen that we collected. This is the temperature of the oxygen that we collected. And the volume is 38.2 milliliters. We need to convert that to liters. So 38.2 milliliters over 1. 1 milliliter is equal to 10 to the negative 3 liters. And that's going to be equal to 0.0382 liters. Oops. Let me bring that down here. So this is going to be equal to 0.0382 liters. Okay, so we've got the pressure of the oxygen that was collected. We have the volume of the oxygen collected. We have the temperature. So now we can plug all of these into the ideal gas law equation and solve for the number of moles of oxygen. So let's go ahead and do that. Okay, so here I have listed our values: pressure, volume, temperature. And so we're going to use PV equals nRT. We want to solve for the number of moles. Why do we want to do that? Is we want to then use the stoichiometry to convert moles of our oxygen into moles of the hydrogen peroxide that reacted. So now we want to solve this equation for N, which is the amount, the number of moles. So in this case, N is going to be equal to PV over RT. So we're going to plug in the pressure, the volume. So the pressure is 0.9671 atmospheres multiplied by the volume, which is 382 liters, divided by R, which is going to be 0.08206 liter atmospheres over Kelvin moles. And then temperature is 299.15 Kelvin. So now you can see that the atmospheres cancel out, liters are going to cancel out, Kelvin cancels out, leaving moles. And so now when we calculate this, we get a number of moles, 0.0015049. So 0.0015049. Let me just double check that. 15049, yes. So this is the number of moles of O2. And so we can convert this to moles of the H2O2, or actually we can convert it to grams. So we can start with moles of oxygen and convert to grams of the hydrogen peroxide, because we need to get the mass, the original mass percent. So in order to get the mass percent, we got to calculate the mass of the H2O2, the hydrogen peroxide that was in the aqueous solution that reacted, and we're going to compare that to the total mass of the solution. Okay, so let's go ahead and use our stoichiometry. So we have 0.0015. Here, let me bring this down a little bit so I'm not running into anything. 0.0015049 moles of O2. Okay, and now we're going to use the mole ratio in our equation. So for every 1 mole of oxygen formed, we need 2 moles of the hydrogen peroxide to decompose. So we're going to put 1 mole of O2 on the bottom, 2 moles of the H2O2 on top. Moles of oxygen cancel out. Now that I have moles of oxygen, moles of hydrogen peroxide on top, now I'm going to use the molar mass to convert to grams. And so I need to look up and calculate the molar mass of the hydrogen peroxide. And when I do that, I get 34.0147. Let me double check that. That is correct. And so then this is going to be grams. And on the bottom, I'm going to have 1 mole of the hydrogen peroxide. On top, I'm going to have grams of the hydrogen peroxide. So moles of hydrogen peroxide cancel out. Now I have grams. So now all I need to do is calculate this. And when I calculate it, I get 0.1033. So 0.10. What did I get? 2377. So 2377 grams of H2O2 in the original aqueous solution. So now that I have grams, and paying attention to significant figures, so here when I calculate this, here's my figures here. So I have 3 sig figs here. Here I actually have, if I go here, I have 3 sig figs here are actually 4, so this would be the last significant figure here, because when I added this to 273.15, I have 1 decimal place here, so I should have 1 decimal place there. This is 3, so this is 4, and then this was the pressure, and that was atmospheric pressure. That was 760. That was 3 sig figs here. So again, this would be 2 sig figs because we're subtracting. Okay, so then I have I subtracted this from 7. Yeah, so I have 3 sig figs here. So, but I only have 1 decimal place. So that would be there. So now here, when I'm multiplying and dividing, I get so I have 3 here. This is going to be 3, and then this is going to be 4, and this is going to be 4 here. So then I have 4 here, and so then underlining this. So that means that this answer should have 4. So now that I have grams, I'm going to take the grams of the H2O2 that was actually in the aqueous solution, and I'm going to then divide by that. So remember, they want percent mass. So what is a percent? Percent is equal to, or let's write it this way. The way you calculate a percent is you take a part of the whole, divide it by the whole, and then multiply that by 100. Why do you multiply by 100? Because percent means per 100. Cent means 100, like century, 100 years. So percent means out of 100. So you take the fraction that you get here, multiply it by 100. So my part here is the grams of the hydrogen peroxide that was in the aqueous solution. The whole is the mass of the solution itself. So this is going to be the mass of the H2O2 plus water that's in the solution. So this is a mixture of the H2O2 plus water. So this is my whole, this is my part. So I'm going to take the part by 0.10237. I'll stop there. Grams of the H2O2, divide that by the whole, which is the 0.85 grams of the solution, and then I'm going to multiply that by 100. So then I multiply by 100. And so when I do that, I get 12.09%. But notice here that when I'm dividing, your answer can only have it has to have the same number of sig figs as the least number of sig figs in your measurements. So here I have 2, here I have 4, so then I'm limited to 2 sig figs. So then the final answer is 12%. And that, ladies and gentlemen, is how you figure out the percent mass of your hydrogen peroxide solution when you know the amount of oxygen that is formed under certain conditions over water. So I hope this is helpful. If you found this video helpful, if you enjoyed this video, then please, by all means, like the video, share the video, hit that like button over there somewhere. Also, do me a favor, hit that notification bell, subscribe to my channel. When you hit that notification bell, maybe make sure that you hit the click all, so you'll be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or a question you need help solving, or if you have a topic you want me to cover, put that down below. I would love to do that for you. Thanks for joining me, and have a great day.